stuff
Yeah.
next week. But then I'll just like the green chem thing's not for it's not on the exam or anything, but just if the undergrads seem interested. Okay. So I'm going to get to it, and I don't know how long this will take, but it's probably not going to take the full time. So I'm talking about cyclic peptides. They're on the assignment. That's what I'm covering. They're also important. So there's three things I want to discuss in this class. The first one is, oh wow, that is a really thick pen. Whatever I did, stop it.
John, I think you haven't shared your screen.
That would also help. That's better.
Yeah.
Yep.
Thank you.
Thank you. I just don't want it that thick. Sorry, apparently I'm having issues with. Okay, I guess it is. I don't really know how to adjust the thickness of the pen. So it's really thick. Okay, you know what? I'm just gonna see if there's an option.
I think if you exit full screen, it might be under draw in PowerPoint.
Yeah, I think you're right. It's just there we go. Yeah, I think I just picked the pen and the pen thickness. Okay. Let's see if this works. Fuck this. I just can't use a pen, I think. Escape.
Is it like zoomed in or something?
Oh shit. Yeah, you know what? That's exactly what it is. It's that when I designed the slide, I made it in centimeters instead of inches, and so it's 8.5 centimeters. You're absolutely right. That is the problem. I was like, I'm going to be really smart, and I'm going to make them all profile, and they'll print nicer. Yeah. Thank you. That is absolutely it.
Damn imperial system.
But just yeah, it's just like yeah, the ratio's right. What the hell can go wrong? Who cares? The ratio's right. No, it matters. There we go. Okay, peptide stability. So when we were talking about peptides to date, we've been talking mostly about linear peptides, and we've been talking about linear alpha amino acid peptides. And so what we have there is, got a peptide. You got some glycines. Let's make a triglycine. That's not glycine. Yes, it is. Okay. So there's three broad classes of peptidases, two broad classes of peptidases, endopeptidases and exopeptidases. So these do exactly what it says on the tin. A peptidase is A's means cleave, like hydrolase or glycosidase or whatever. So a peptidase breaks up peptides. An endopeptidase breaks up a peptide on the inside of the peptide. Excuse me. An exopeptidase chews the peptide from the outside. I'm going to make this one peptide longer, I guess. And just for shits and giggles, I'm going to make it alanine because why not? So endopeptidases are normally specific for a 3 amino acid sequence. Some of them are specific for a 2 amino acid sequence. So what they're looking for is they're looking for two specific amino acids, or maybe three specific amino acids in a row somewhere in a peptide, and they're going to cleave there. So a lot of endopeptidases have specificity. There are some non-specific, but not many, but not as usual. The point here is that you can get, normally the role of the endopeptidases is when you have a polypeptide, like, multiple, it's a protein-based protein pieces, and it's comes off the ribosome as one long peptide. And then the endopeptidase goes, okay, I know that I need to cut right here because now I'm going to release two different proteins that are going to do their thing. When they're attached together, they're not. That's how they're transcribed off the ribosome. But um, they're not useful that way. I need to cut them. And so endopeptidases do tend to be specific for a sequence. The exception to that is when they're in a lysosome, which is this compartment in a cell that just breaks everything up. And the endopeptidases in there tend to not be very specific. Exopeptidases are almost always not specific. Chew peptide from the outside. So you have them. You have different ones. You have some that chew from the N terminus, some that chew from the C terminus. And the overall idea here is that your body is constantly making proteins, keeping them around for a few hours to days, depending on what the protein is, and then destroying it and making more, because you control your physiological response in a given cell by how many of a given protein do you have. Like, if you're mounting an immune response, you're going to want a lot more immune receptors on the surface, but once that emergency is over, you're going to want to get rid of all those immune receptors. So proteins are constantly in a churn. And the endopeptidases and exopeptidases are basically the cleanup crew, and they break them back down to the amino acids, which then go back to the ribosome, get reloaded on some fresh tRNAs, and away you go. You've got some new peptides. So peptides are meant to be transient. Proteins are meant to be transient. The problem is when we want to use a peptide drug, and almost everything we're talking about is synthetic peptides, and you're not normally making a peptide to do something non-biological. There are a few exceptions, but for the most part, you're making a peptide so you can put it into somebody and do something. And you don't want your drug that you just spent all this time making to be broken down by the first exopeptidase that shows up in the blood. So we've got a problem here. Now, your body doesn't care about that because it's constantly making new stuff. But if you're injecting drugs into somebody, you want to make sure your drug survives long enough to do its thing. So we have this peptide stability problem. So how do we overcome that? How can we make a peptide more stable? And I'm going to say that there's this is a little lie, but it's good enough for this course. There's more than 3 ways, but 3 main ways to stabilize. One, mess with the side chain. I realized I make these lectures public so that theoretically anyone could find these, so I'm really trying to keep the swearing down. So what does this do? Well, if you mess with the side chain, you're going to mess with any endopeptidase, because again, the endopeptidases are looking for specific side chains. So if you're modifying the side chains around there, for example, if our endopeptidase cleaving here, do that in blue, is looking for 2 glycines next to each other, and suddenly one of those is not a glycine, it's not going to be able to cleave that. So affecting your side chain can affect the stability. That's interesting, but often you don't really have a choice. Like, you have a side chain there for a specific reason because it's part of either catalytic activity, recognition activity, or binding activity of the peptide to the target. So not always a choice. If this course was about 3 weeks longer, we could have talked a lot about using non-canonical amino acids for this, which is something I'm really interested in. A non-canonical amino acid is anything that's not the 20 amino acids. we didn't really talk a lot about that. There's two amino acids, homocysteine and ornithine, which are not part of the 20, but they're kind of found in a lot of biology. And they're like bacteria use them in their main genetic code. So they're kind of weird. But so normally when I'm referring to non-canonical, I mean like artificial amino acids, something weird that isn't found in nature anywhere. Two, um, you can play with the backbone. So your enzymes are looking for alpha amino acids. And so what if you don't give it an alpha amino acid? So the two I want to introduce are the idea of peptoids and beta amino acids. And number three, cyclize. If you've got a cyclic peptide, you don't have an end for the exopeptidase to start chewing on. So then you only need to worry about the endopeptidases, which is actually a much smaller problem generally, because again, they tend to be very specific, and unless they're in the lysosome, and if your stuff gets into the lysosome, you've got bigger problems because it's got all sorts of enzymes in there to break things up. That's what its job is. So we've got three ways to kind of protect our peptide. We can play around the side chain. I'm not going to talk any more about that. We can change the backbone to incorporate peptoids or beta amino acids. There are other things we can use too. And we can cyclize. So I'm going to start with number two, and then we'll move on to number three. So what the fuck's a peptoid? So a peptoid is, I'm just going to show the three most common. There's going to be one more. I guess I'll talk briefly about two. So this is a peptide. A peptoid, I'm going to substitute this. I'm sick of drawing alanine, so we'll make it serine. Peptoid is if I take that side chain and I stick it on a nitrogen instead. So I kind of got glycines with alkylated nitrogens. So a couple things about the peptoids. You can make an entire peptide out of peptoids where every single residue is a peptoid. That's going to have a problem. It's feasible, but normally you won't want to do that. Any idea for why you might not want to do that?
Sorry, sorry. Could you repeat the question?
So you can make an entire peptide, like 30 amino acids, entirely a peptoid with 30 peptoid residues, where all the alkyl side chains have been shifted onto the nitrogen. Why might
But
that be problematic?
that would be quite unstable. It would break down.
It's actually really stable metabolically, but I like
Oh,
unstable. In what way is it unstable?
Uh,
intramolecular reactions could happen. I don't know. Looks like.
you have.
Oh,
Uh, okay.
You've lost all your hydrogen bonds. So whenever you think about how a peptide organizes itself, if there is any secondary structure, if it is going to fold over itself, if it is going to interact with something else, it often does that. Like I'm as guilty of this as anybody. I often think of the backbone is interesting, but the action is all happening out on the side chains. And I know that's not true, but I still believe it. Often what's often happening is actually the side chains. Normally what they're doing in almost all peptide structures is they're orienting the backbones around so that you're getting your secondary structure. And your secondary structure is almost entirely caused by hydrogen bonds between backbone amides and backbone amides. The side chains are just kind of there. Um, and they help fold this beta sheet to the left or that alpha helix to the right, but they don't make the alpha helix or the beta sheet. That's formed by the backbone residues. So when you remove those backbone hydrogens, you actually affect a lot of protein peptide interactions and peptide and the intramolecular peptide interactions. So you probably don't want to make the whole thing out of peptoids, but you can replace some residues with peptoids. And even replacing one or two can really confuse the peptidases. And then the other type of molecule I want to talk about, which also really confuses the peptidases without surrendering that. Just trying to draw it consistently. So it's called a beta amino acid. And so what you can see we've done here is we suddenly have an extra CH2 between the acid, there's an extra two methylene groups in there. These guys are new. So again, now we're confusing peptidases, right? Because they're looking for an alpha amino acid. They're looking for a spatial orientation of that specific side chain they're looking for with respect to the amide on each side. And now suddenly you're fucking up their spacing because your amides are an atom further away. So their catalytic system is designed for a certain spacing, but now you've broken that spacing. You've made it further. And so it can no longer cleave the bond. The problem, of course, with this is it messes up spacing. So if you're trying to get biological activity, this can be problematic. And sometimes it really affects things that don't have any biological activity. I've never published this, but I did my PhD on glycopeptides and ice recrystallization inhibition. And the alpha amino acid glycopeptides I made are really, really good ice recrystallization inhibitors. As soon as I throw a beta amino acid into there, they suck. And it doesn't matter where I put it. So it's not like it's interacting with ice. It's not even interacting with a biological system, but the beta amino acid disrupts structure enough that we lose activity. But it would stabilize it. So you do have to be careful. Again, you might not want to make an entire peptide out of beta amino acids. You can sort of make a mixed one where you throw in the occasional beta amino acid where it doesn't matter. This is a strategy we might actually be using to stabilize some of the COVID drugs we're making in the group. So peptide, peptoid, beta amino acid. There was a third thing I wanted to talk about. Oh, the third example I want to talk about is quaternization. So this is a different kind of quaternization from that term everywhere else in chemistry, which means make the nitrogen have four alkyl groups on it and positive. That's not what's meant here. What's meant here is that I basically add a second methyl group to the alpha position. And again, what we're doing here is we're going to confuse the enzyme because the enzyme is looking for specific sizes. And normally it needs to get close to that. Like it needs to get something close to the amide. So normally what it's doing is dodging the side chains. But now we're making it impossible for it to dodge side chains because there's side chains everywhere. Because you got stereochemistry going off in every which direction. There's not sort of a flat, easily accessible side of the peptide anymore. And so again, we're confusing it. So we can modify the backbone and play with this. Of course, everything you do to the backbone can then affect the overall stability, the overall efficacy of the peptide, because now it's not the same peptide. And so if you designed a peptide to do something, and now your peptide is different, it might not do the same thing. Like my peptides didn't work as ice recrystallization inhibitors. So what this leads us to is cyclization. I'm not going to have time to do this. I'm just going to go back a slide because I want to just, the only one I'd really talk about here is this thing because it's really, really cool. I hope I'm spelling this right. You know what? I'm going to just check this on Google. I really love this reaction. It's a good way to make, you can make the beta amino acids from any of the alpha amino acids. I'm just going to make sure I spelled that right. Well, I did. Okay. I think there might be an assignment question that circles around beta amino acids. So it's not a bad idea to look up the Arndt-Eistert homologation. I love that reaction so much. It's very clever. It's very easy to do. And it involves diazomethane. So another option is cyclization. So let's say you have a linear peptide. And then you've got a protein. Protein. This looks a bit like a boat with a wavy. Actually, it looks like some sort of hieroglyph. So you got a peptide, you got a protein, and they're interacting with one another. Okay, so everything we've done so far is going to affect that interaction because you're either sticking in non-canonical amino acids to change the side chain, or you're playing with the backbone. What that's going to do, of course, is that's going to change the spacing along the peptide. Or in terms of quaternization, you're probably going to change conformation a little bit because some of there's this extra chain in there. So either way, you're going to mess with it. But a way we can sort of keep this thing intact while stabilizing it, not stable, linear, is to cyclize it. So we have the same enzyme. Don't do whatever I just did. I have more or less the same peptide, but now I cyclize it. This is arc. And so what you've done here is if you design your cyclic peptide properly, you don't induce any strain on the binding side. So this basically fits exactly the same, but now there's no end. So now it's perfectly protected from exopeptidases because there's no edge to the peptide because it just goes around in circles. And then you have this round thing over there, which, yeah, it's there, but it doesn't matter because it's not interacting with the protein. So you're not sacrificing any binding. You're not sacrificing the specific interactions that you want to target, but you're protecting your peptide because it doesn't have an end, and so the exopeptidases can't get to it. Okay. So what I want to talk about is a few different ways to cyclize a peptide. So one is very, very simple. Let's just take a peptide And we can treat that with, just coupling agents. It's got an acid on one end, it's got an amine on the other. And you cyclize it. And when you draw it that way, you're like, why is this hard? Like, of course, it's got an acid, it's got an amine, it cyclizes. Why are we even discussing this? This isn't challenging. Okay. So why are we discussing this? Why is this challenging? What are the potential problems?
You have several carbonyl groups that the amine can attack.
You do, but the other ones are all amides, right? What do you mean other carbonyl groups? Like on the same molecule?
Like, yeah, like what stops it from attacking like in the middle of the peptide rather than the end?
Well, you're going to activate, because the HBTU is going to activate this as an activated ester. So it's going to make this a lot more electrophilic than any amide in the middle of the polypeptide. So that's not a concern. You're not really going to have this. Otherwise, we'd be fucked every time we tried to make any peptide because it would just all react with itself. The amides within the peptide are very stable.
Okay.
So this coupling agent, how does it ensure that this peptide is going to be cyclized instead of two peptides combining together?
Exactly. Exactly. These are the problems. So this is not anything specific about peptides. This is a universal challenge in macrocyclization. So when I say macrocyclization, what ring sizes do you think about?
48 plus?
48 plus. Wow, okay.
Okay.
I think I draw that line a whole lot smaller than you. Um, I'm pretty happy with, about more than about 14 plus.
Okay.
Um, but I'm not saying you're wrong. There is no definition. Everyone's line's going to be a little bit different. I start thinking that things start getting really kind of tricky. Like you start really having trouble. You honestly start having trouble at like 8 and above. Like 5, 6 go like a shot. They intramolecularly cyclize. There's no challenges there. You start running into problems as they get bigger. But this is so how do we address this problem?
You protect? No.
No, that's where you
No.
can't, right? Because
Yeah,
they
we
all need
can't.
to be reactive.
Do you need like a catalytic surface or something?
That can help, and actually, that is a way around it. And you're kind of pointing towards one of the solutions that we have that's unique to peptides.
Um, is there bacteria involved again?
No, no bacteria.
Okay. Um,
Well, fundamentally, what what factors play into the rate of any reaction?
Substrates. So do we control the reactants amount?
Do you want to be a bit more specific what you mean by amount?
Um, okay, I'm thinking.
So rate equals, let's just say A goes to B. What's the rate law for that?
Isn't it K KB.
Right. Okay. Ka.
Oh yeah, sorry, that's what I meant.
Yeah. Okay. So what factors go into determining the rate?
Concentration of reactants.
Yeah. And what does K represent?
Um,
Big picture. Let's take a step back and think about what K really means.
Um, how fast the conversion is?
Yeah, it's kind of like an inherent reactivity of the system, right?
Yeah.
It's kind of the activation barrier of the molecule. It's not the activation barrier, but it's associated with the kinetic activation barrier of the transformation. So K is kind of the inherent reactivity of the reaction you're trying to do and the concentration. Okay, now let's think about that. So let's say we're doing a cyclization versus a dimerization. So in a cyclization, I'm being told to please get my dog. Can you hang on a second? I'm just going to go rescue my dog. I will be right back. Think about the difference. So I'm going to leave it actually here as a question. Hopefully, you guys can discuss and figure this out. Think about the how this plays into how we can really affect these kinds of chemistries.
Any ideas, guys?
not really. I'm kind of confused where he's going with this.
Yeah, I have no idea.
I think um, if we
Okay, I'm
so
back. I found him.
active,
Sorry, go on.
so if you play around with the overall energy of the system, more like if we provide the environment in such a way that cyclization is more preferred over dimerization.
Okay, so how do we do that? I agree with you. And actually we're going to get into a bunch of ways to do that. But how do we do that?
Can you manipulate, like, just conceptually? Can you manipulate K, like little K?
Yeah, we can manipulate K, but I'm actually going to think more about the concentration of A. Okay, because let's think about in a cyclization. Let's say we have one molecule. So sit in your
Oh,
room, like right now. Just
um,
look around the room you're in. You've got a molecule in there. Actually, no. What you've got. Okay, this is Paul. I know you've heard my ninja with swords analogy because I used that in third year. Have I used Susanna and Samurai? Have you heard my sword ninja analogy?
No.
I haven't.
Okay, so let's imagine for a second for a dimerization. You need two molecules to come together. Okay, do you
Yeah.
agree?
Yep.
Okay, so molecules are blind. So I want you to imagine two ninjas, both with swords and both blindfolded. And what they're doing, I'm going to turn my camera on, is they're blindfolded and they have their sword and they're just doing this. I'm actually going to walk around my room and trip over something. They're just walking around, slashing their sword. Okay, so you've got two ninjas walking around doing that. Now, my office isn't very big. So if I have two ninjas in my office walking around slashing their swords, it's not going to be too long before one of those ninjas cuts the other ninja. That's a reaction. Because the ninja needs to be swinging a sword with enough force to be able to have the reaction occur. And the ninja needs the right directionality in that they need to be facing the right direction. So the orbitals need to be pointing in the right way for the cutting to happen. It kind of falls apart because it doesn't really matter what direction the other ninja is going. You don't need orbital alignment. Like if you're cutting a ninja with a sword, it doesn't matter if you're cutting them in the back or the front. Like they're cut. So we've got two ninjas walking around my room. Now, they're at so the concentration I've got is two ninjas per room of this size. Now, if I doubled the size of the room by knocking out this door and or this wall into the bathroom next door, then I saw those two ninjas, but there's more space. So, do you think that my rate of ninja cutting is going up or down?
Down.
Yeah.
Right, exactly. Right, it's going down because they've got more space, so they're not going to cut each other as easily. Okay, that's cool. So if I decrease the concentration of ninjas, I'm going to slow down the rate of ninja slashing.
Yes.
Now, let's say I want to cyclize. So what I'm going to do is I'm going to take two ninjas and I'm going to tie them together with a rope. I'm going to see if Finn brought his rope downstairs. He did not, because otherwise I could do this with my dog dragging me around the room. So we're tied together by a rope, and we're still slashing our swords as two ninjas, but we're tied together by a rope. It's going to take a certain amount of time for us to cut each other in this room. Now, if I knock that door down, that wall down, my room is double the size. How does that affect the rate of? How does it affect the actual time it takes for the two ninjas to cut each other?
It'll take longer.
No, because they're held together by a rope. They can't wander away
Quicker.
from each other.
Oh.
Because in the bigger space, when your two ninjas are not tied together, they can wander away from each other. But if the ninjas are tied together, it doesn't matter how big the space is. Right? Like you could have the two ninjas walking around Maple Leaf Gardens or, the Joe Louis Arena before it was knocked down. And if you had the two ninjas not tied together, they take forever to find each other. Those places are huge. But if they're tied together, it wouldn't matter if they're in a small locker room or like the Dubai airport. The amount of space is irrelevant because they are tied together.
So do we want to dimerize first and then cyclize?
Normally you just want to cyclize, you don't want to dimerize. But in a cycle, what you're thinking of here is your ninjas are the amine and the carboxylic acid. What we want is those two pieces to come together, right? And they're tied together by a rope. And I'm using the wrong page, so it doesn't make any sense. So the amine and the carboxylic acid are each ninjas, and they're slashing. And if they're tied together by a rope, they'll come together and they're able to make the bond. If they're dimerizing, it'll be this amine with a carboxylic acid on another molecule. And those will be two separate ninjas not tied together. So if I dilute my reaction, I make it harder to dimerize, but I don't affect the rate of cyclization. Like cyclization happens the same whether there's 1 molecule per liter or 1,000,000 molecules per liter. It's just that dimerization is going to happen a whole lot faster at 1,000,000 molecules per liter than 1 molecule per liter. When I demonstrate this, when I'm lecturing in one second year class a few years ago, I actually had play lightsabers and had students do this in front of the class, which was a lot of fun. But then one of them tripped because they were blindfolded, and I haven't done it again. They were good sports about it, but still.
A liability.
Yeah, it's a liability issue. I still kind of want to try it again. So maybe what I'll do is maybe we'll do it in a field, and I'll grab some undergrads from the group to restage this.
Lay the floor with yoga mats. That's fine.
Sorry?
Lay the floor with yoga mats.
Yeah, we'll do it outside on a grassy thing, like a soccer field, and we'll give them pool noodles. Okay.
I would want to watch it.
Sorry?
I would want to watch it.
Yeah, I'd want to watch it. We could probably charge admission. So, high dilution drives cyclization. So that's one thing we can do. The other thing is, as we were sort of saying, I think it was Samra who was saying, can we just change the conditions of the environment to affect K or this? And what we're really interested in here, of course, is, again, it's kind of coming down to this idea we're talking about multivalency when we're talking about the dendrons, is what we'd really like to do is get that amine and carboxylic acid close together. Because if they're forced close together, then their local concentration is really high and they're much more likely to cyclize because they're always close to each other. So, in general, amino acid 6+ amino acid peptides, so I guess greater than 6 amino acid, maybe is a better way to write it, are easy to cyclize. It's not that they don't dimerize, it's just that the cyclization is not a bitch. 3, 4, 5 amino acid cycles are a bitch. They are really hard to cyclize. And that's because of the strain is not favorable because they start getting in each other's way. You start getting steric hindrance. When they're bigger, the side chains are no longer in everyone's way, and it adopts all the conformations, but there's nothing stopping it wrapping around making a cycle. But 3, 4, 5 amino acid ones are actually really unfavorable. And you think, well, that's not very big. But just remember, 3 amino acids is a 9-atom system, which is no longer very favorable for cyclization, and then 12 and 15. So you're starting to you're in that nasty zone where your cyclization is bad, and now you have all this extra steric stuff that's banging into each other. So these things, they tend to adopt sort of extended chains. They don't tend to fold back over each other. So how do you get around this? Well, one way you can get around this is to use the proline effect. So if you have, a 3 amino acid sequence, that's not going to be an amino acid. And I know that proline is Paul's favorite amino acid. But there's no proline here for now. Isoleucine. Just for a change. What we want to do is we want to cyclize. It's kind of seeing out as an extended chain. This is 1, 2, 3, 4, 5, 6, 7, 8, 9 atoms, which is not a favorable cycle, right? We want 5 or 6 for good kinetic cycles. 9 is a bitch. 9 is even worse when you have these kinetics in there, or these sterics and stuff. But if we swap one of those amino acids for proline, I'll keep the glycine on here. Suddenly, proline causes a turn. So it can no longer extend out. It now actually automatically has a fold in it. Now your ends are not able to access all those extended conformations. They're going to be held a little bit closer together than they would otherwise be because proline forces this turn. It does not allow you to extend out because it's proline. Now, it's still really hard to do 3 amino acids. And of course, you're stuck to this only works if you've got a proline in your peptides. If you don't have proline in your peptide, you can't use proline. So this is where you can get the idea of pseudoprolines. This is actually what this is Sanaz's PhD thesis. And the idea here is that, well, you don't need real proline. We can have sort of fake prolines. So there's your carboxylic acid. There's our nitrogen. And if we look at serine, well, we can actually just tie it up. Now, what we've generated there is we've generated that pseudoproline. We have that 5-membered ring. We've kind of induced the turn, but we don't have proline. And so that's why they're called pseudoprolines. So you can do this with cysteine and threonine. And what Sanaz is doing for her PhD is trying to spread it to all the other 17 amino acids, or 16 amino acids, 15, because I guess you can't do it with glycine either. Everything else except for these guys in proline. And the idea is that we can force a turn and we can force the parts closer together, so we're more likely to be able to make the bond. That's okay. But that's kind of modifying the environment, right? We're modifying our structure to make this happen. No, don't attack the desk. No. Okay. So another way that we can kind of handle this, and I think this is really elegant, is, I'm trying to see if I have the name associated with it. I don't. I'm sorry. I just have the idea. Is, let's say we take an amino acid, like a peptide, and I'm going to just throw a methoxy ester on one side. You know, you think I'd be better at drawing these goddamn things after all this time. Yes. I don't know, chuck on some things, whatever. So again, we're in this danger zone of this being a 5 amino acid peptide, which is tough. Again, we're close to 6. We're almost at that magic number where we don't need to worry as much about sterics. We're still at 5. The chemistry is just transamidation. You'll also see this if you want to look it up. You'll call it macrolactamization because it's a lactam being an amide in a ring. Because amide in a ring, I don't know why anyone gets upset about that, but they really like lactam instead of amide there, but it's the same goddamn functional group. Chemically, nothing wrong with that. Thermodynamically downhill, you're making a much stronger amide bond from a weaker ester bond. It's awesome. The problem, of course, is this whole dimerization thing. And so what somebody noticed is what happens if I just chuck in a whole lot of sodium? Well, what's sodium going to do? So you might know of crown ethers. I actually know some of you are intimately acquainted with crown ethers. That's crown 5. Actually, that's perfect. I think it's 12C5, right? 1, 2, 3, 15C5. Finds sodium really well. It's a good sodium thing. 18 crown 6 is good for potassium. And what we have there is just electrostatic interactions between the oxygens of the crown ether and the sodium. And that's because the sodium ion is positively charged and the oxygens are electron rich. So what somebody thought is, well, peptide is kind of like a crown ether. So if we have the sodium plus here, that's also a glycine. So we got 2 glycines. Got a phenylalanine. Note that what I'm doing here is anytime that the bond is like this arrow points down, I have a down wedge because that's the right amino acid. Anytime it points up, it's an up wedge. When I'm going with nitrogen on the left, carboxylic acid on the right. That's just the way it is. Otherwise, you're drawing the enantiomer by accident, which is not what you're intending to do. And now it doesn't really matter how big the cycle is. This is actually going to work out kind of nicely. I messed something up. Okay, I managed to get. Okay, I managed to get myself confused up here. Um, you get the idea. Okay, but the overall idea is that we're bringing these guys in close proximity, and so we get that cleavage because we wrap our peptide around the sodium atom ion. And so again, what we're doing here is we're bringing the ends in close proximity, and what we're doing with that effectively is we're increasing the localized concentration of the two pieces. We're basically either, you can think of it either as literally you draw your ninjas, instead of it being a rope, it's now basically a stiff piece of metal which is in a semicircle, so the ninjas are almost facing each other, slashing at each other. Or you can think that you're shortening the rope. Either way, you're increasing the rate of the reaction. And because you have this localized concentration, it's still a movement, but the amount of space they have to move in is a lot smaller, so they're much more likely to whack each other. So this is templating. Very efficient for medium-sized rings. Doesn't get used as much as it should because this is just clever. And everyone thinks it can't possibly work that well, but it really does. It works great. Okay. The next thing I want to talk about with cyclization is you know what? I'm going to. There's also different chemistries we can discuss. They don't really matter. The big thing that I think I really want to touch on for the no, there's one more. There is one I'm going to talk about. So I'm going to talk about a Staudinger ligation. So this is messing with K. Doesn't solve the concentration issue. You still have a dimerization problem, but you get this can be an effective way to do it. So let's say you have you have a normal peptide. There, I'm terminating my normal peptides unusually. There's a peptide, then there's a C-terminus. So what we're going to do is two modifications. One is we're going to first treat this triflic azide. What is that? I'll actually just draw out the reaction conditions first. So in the first reaction, it's triflic azide. That's really specific to convert amines into azides. So mechanistically, there's multiple ways to introduce this piece, but we'll cheat and use this. It's not the best way, but it's good enough for now. So triflic azide. Maybe I should draw out the triflate. That. I'm just going to draw the resonance structure. I should have just drawn resonance structure to begin with. It's just I can't. I get very confused. I can never draw this resonance structure without drawing the other one first. So if you have this, and you have an amine, that happens. So what's happening here is you're transferring a diazo group, two nitrogens, onto the other nitrogen, and you're releasing a triflamide. And because that triflate group is so good at stabilizing negative charges, it's actually possible to do. So this goes to azide. So we protected that side. Now we've gotten rid of that amine. Now we do a coupling. You're going to activate the ester, and then we're going to add in this thing. The nucleophile is the SH. And then you heat. So I don't know how many of you guys know the Staudinger reduction.
I've heard you say it before. I don't remember what it is though.
Okay. Phosphorus is an amazing nucleophile for targeting very specific electrons, leaving groups, and the one it really likes are azides. It's a magical reaction. It is incredibly selective, and so it's going to ignore everything else in the molecule except that nitrogen. So It's very reactive. It's a very fast reaction, especially when you heat it. But it's stable enough at room temperature that's not going to do it beforehand, so you can put the damn thing on. So that's all going to wrap. I'm going to start a new page. So we're going to have a ring. I want to make sure that my ring is accurate. Nitrogen, carboxylic acid, sulfur. So once we make this bond, sorry, I'm gonna have to draw it out because I'm gonna confuse myself with that. You know what? I'm going to draw from a slightly different resonance angle because I don't like that bond. I don't like what I'm going to do to that poor negative charge. This isn't going to upset me as much. So let's say we have that. We'll draw that. It's the same thing, but it's just I don't have to draw a charge I don't want to draw. We made a phosphorus nitrogen bond. Sorry, I'm going to lost Samara. That's not going to be particularly stable. Remake nitrogen gas. You have an N minus attached to a P plus. Really should draw this curve last. I never learned though. Plus nitrogen gas. So that's what makes this so favorable is the Staudinger ligation. And it's a ligation because we're ligating two things together. Has done that. Okay, but that really doesn't help us at all because we have stuff here that doesn't make a lot of sense. So let's think about what happens here. So we have a nucleophilic nitrogen, 1, 2, 3, 4, 5 atoms away from a carbonyl that's activated because it's attached to a sulfur, which is a damn good leaving group. So if we do that, I guess this should have just been diphenylphosphine. Nitrogen, blah, 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 phosphorus, blah, 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 sulfur, S minus. And now we're starting to get closer to being done. So what is a little weird here is we're going to tautomerize. And again, this has got to do with where that negative charge is. It's not in a great spot. It's a little far away. So we're going to move that negative charge right next to the phosphorus to make the ylide. Oh, we generate a cyclic peptide. Now it looks like we do have some strong reactive species in here. We got an N minus, we have a C minus, we got P plus. There's a lot of arrows, but it's all happening. It's all intramolecular. It's all happening, or proton transfer. It's all happening right within the same molecule. So it doesn't have any time to interact with anything else. So once you get this initial cyclization to occur here, it's all really fast downhill towards that product. There's nowhere else for it to go. It's just going to go to product. It's got no choice. So do you need to use a stoner ligation ever? It's kind of a bitch to draw, but they work really, really well, or so I'm told. Again, like any Staudinger reaction, it never works for me. But it does theoretically do a really good job. So the last thing I want to touch on with peptide cyclization is I need to add more slides. Yeah, keep, please. That'll do us. So the last thing I want to add on to this is something unique that we've got. So again, our problem with peptide cyclization isn't so much that we don't have good ways to make amide bonds. We've got lots of good ways to make amide bonds. It's that we have this dimerization issue. So one option we have is on bead cyclization. So again, this plays onto the idea of we've got our bead that we're using for solid phase peptide synthesis, and we have the peptides here coming off of it. And so what you can do is you can make sure the peptides are spaced out enough from each other that they actually can't reach the next peptide over. So the peptide can't physically do a dimerization. I guess the ninja analogy of this is if I have those ninjas on a string and I pin one ninja to the wall and staple them to the wall, it doesn't matter how many pairs of ninjas on strings I pin around the room, they actually can't bump into each other because one of them's pinned to the wall. It's going to be a matter of time before the free ninja swings around and cuts the guy who's on the wall. And that's basically what's happening here. So the problem is that you need the carboxylic acid to attach it to the bead. So if we, zoom in on this, there's a bead surface, whatever. And Wang resin, whatever the case may be, whatever your linker is that we talked about. This is not an activated ester. That's really important because if it is, your peptides would always be cyclizing whenever you're trying to make them. You'd be fucked. So it really is important that this is not going to do any chemistry. But that's my carboxylic acid. there's a problem here because I need a free carboxylic acid. Okay, so let's think about I'm going to draw a cyclic peptide. And I'll just use the codes. Okay. Let's say I want to make a cyclic peptide. If it's a linear peptide, I don't have a choice which residue is attached to the bead. The C-terminal residue is attached to the bead. But a cyclic peptide doesn't have a beginning and it doesn't have an end. Like, by definition, it's a cyclic peptide. Can I make use of that with this peptide? I guess you need to know what the amino acids are. So that's aspartic acid. I really hope I'm right on that. And so if we think about what the aspartic acid is, we'll draw it out. It's got a carboxylic acid side chain. Nowhere in the rule book does it say what acid needs to be attached to the linker. So, what if I do my disconnection right here? So I have my bead, and I don't attach to the main chain carboxylic acid. I attach it to the carboxylic acid of the aspartic acid side chain linker acid. Protecting group, nitrogen. Now that's attached to a histidine, that's attached to a leucine, that's attached to an isoleucine, to an alanine, to a phenylalanine, to an asparagine, which then has a terminal NH2. Now suddenly I can cyclize because I've cheated. I've used, it says attach. I always write attack, so it looks like attack. I've cheated because I've used the side chain to attach myself to the bead, which leaves the main chain open. And so I can now cyclize here using HBTU, HCTU, whatever the fuck I want after I deprotect that R group. And so any cyclic peptide that has either a glutamic acid or an aspartic acid in it, well, you can do this. And if your cyclic peptide doesn't have an aspartic acid or glutamic acid in it, could it? Like, really, would it hurt the biological activity if you suddenly put one in there? So this is a way around this problem. I guess we could talk about some disulfide bridges, but I really don't want to. But that's another way to cyclize peptides is to use disulfides. The problem I've got with disulfides and why I'm not focusing so much on those is because they are reversible. Whereas all the chemistry we're talking about here is much more covalent, permanent chemistry. Whereas disulfides are, you know, It's covalent, I guess, but you break the disulfide, you form the disulfide. It's confusing. So I think that's where I want to leave it. This is an important component because what it means is no worry about dimerization. I'd say that 15 years ago, dimerization versus oligomerization, solution phase cyclization of peptides, that was a lot of words, but hopefully it all made sense, was a major challenge and a major concern. But over the last 15 years, almost, I want to say like 80% of all cyclic peptides I've seen have been synthesized on bead using this kind of strategy, just kind of bypassing that whole dimerization thing. Your yields might not be as good. You might be a bit more constrained in your choice of solvents, blah, blah, blah. But if you don't need to lose 60% of your material to dimer, fuck it. Like, take that every time because you're not going to get any dimer. You don't need to worry about dimer. You're only going to get cyclic peptides. So on bead cyclization, I think, is kind of the state of the art of peptide cyclization. And it arises naturally out of the fact that we do so much of this stuff on bead. The other stuff is still useful, though, controlling concentrations, because sometimes, for whatever reason, you are cyclizing off bead, or you're doing some other kind of macrocyclic cyclization. But if you do need to do a macrocyclic cyclization, it's giving you grief and pain and suffering, and it's off bead, even if it's not a peptide, you might want to consider sticking it onto a bead and then try and do the cyclization. And as I am saying this, I'm realizing I should have a conversation with Sarah and Sanas about some of their cyclizations that are giving them some trouble. Because maybe we should be doing those ones on bead.
Would you not have could an amino acid, or I guess a peptide chain from one bead attack another bead? Like, because you have multiples of these things floating around, don't you?
Yeah, so I've drawn the bead like this, but normally what we're looking at, that's a really good question, by the way. So I'm lying when I draw the bead like that, because what a bead looks like, if we actually really draw a huge bead, is it's a porous material, so it's got these huge gaps in it. And what's normally happening is the peptide is growing inside these gaps.
Okay, that makes more sense.
So sterically, I'm not aware. Like, theoretically, I think you could covalently bind two beads together. I've never seen it happen, because the size of the bead is so much bigger than the size of the peptide. Like, the beads are macroscopic; you can see them, right? Like, I don't know if you've seen these peptide synthesis beads, but they're probably on the order of 100 microns or bigger, maybe up to a millimeter, depending. Whereas a peptide, even a really long peptide, we're talking a few nanometers. So the bead is just so much bigger than the peptide. So the peptides are kind of growing within the beads. Um, and this isn't the reason why the beads are porous. Because I think the sterics of the beads bumping into each other, like the beads are so big, it wouldn't really cause an issue even then. It's more that these porous beads have much higher surface area, so you can get a lot more peptides on them than just if you're just coating the surface of the bead.
That makes sense. Yeah.
Yeah. No, that's a really good question.
I assumed that, like, I assumed that there was a reason. I just wasn't really sure why.
Yeah. Now, of course, you got me thinking, Paul. If we could, like, join two kind of glass or metal nanoparticles together through covalent bonds.
We could make a game of telephone, an atomic game of telephone, like the tin cans.
Yeah, the problem with the beads is they're three dimensional, so the damn thing would just form a mess, right? Like, it would just it would make a net. It wouldn't be a linear thing. It would be like a cluster, a ball. You make a bigger bead. um, sort of get these gels that you get when a polymerization goes bad and starts cross-linking on you.
It's almost as good of an idea as um, molecular chess.
Yeah. Well, I know. Yeah, I could see it being sexy if we could figure out a way to make it linear. Um, really low loading. Yeah. Okay. I think that's where I'm drawing a double line under the course. Starting subtitles. Don't start subtitles. Oh, got that right. That's good. Okay, any other questions about this material? I guess from either one of you guys.
Uh, no, I think I'm good. Are you? So, sorry. Oh my god, I can't speak today. Next on Thursday, are you going to be like here in the Zoom on during class time, or?
No, but if anyone wants to talk, I can arrange something. Probably for Friday. I just have a grant going in Thursday afternoon, so I'm probably going to reserve that time. But if somebody wants to talk on Friday, I definitely can.
Okay, I just have a few questions about like the assignment, some of the assignments, and
Yeah, so next Tuesday, I'm definitely going to be doing that. But maybe I can arrange a time on Friday where I can sort of say, hey, if anyone wants to drop by, we can all go through them together because I won't need to be saying the same answers multiple times.
okay, yeah, Tuesday's fine. I just wasn't sure when you were
Yeah,
doing it.
that's fine. Um, I'm also, yeah, but I've got a few minutes if they're quickies, I guess.
Wait, next Thursday is the exam, though.
Right. So if you
That's
want to meet on
not.
Friday instead of Tuesday, that would help.
Oh, okay.
Yeah.
Are all the questions fair game, like the midterm?
Yeah, the midterm questions are all the questions from the midterm are fair game. There's one question which I withdrew. I think I said assignment 3 question something because it involves C glycosides and we didn't cover that at all. But everything else is stuff that it's an extension of stuff we've covered. Like the questions are blatantly unfair, but you have as much time as you like to think about them and use resources and stuff. And also ask me questions if you're not sure about the right direction to go in on them.
Okay, sounds good.
Yeah, like it'd be stupid unfair to be on an actual exam blind. Like it'd just be so ridiculous. But the goal here is so that you guys can start, thinking about these things. And I wanted a bit more guided than some of the courses I've had where I've had these blatantly unfair questions where, it's the questions really have nothing to do with the course material at all. My nightmare course was stop recording.